Good morning. I welcome you all to this session of fluid mechanics. Well, last time we discussed the different types of flow meters, namely venturi meter, orifice meter, and flow nozzles. Today we will be discussing another type of flow meter which measures the fluid flow in a fluid circuit, that is pitot tube. This pitot tube measures the fluid flow by measuring the fluid velocity, the local velocities, and then from the velocity it determines the fluid flow rate. And this determination of fluid flow velocity to measure the flow rate by a pitot tube is based on the concept of static and stagnation pressures. So therefore, we should first know what are meant by static and stagnation pressures. Now, static pressure is nothing but the hydrostatic pressure, that is the pressure which is exerted when the fluid is at rest. As you know that in hydrostatics, that when the fluid is at rest, the pressures at each point is same from all directions, is a Pascal's law, and this pressure is the result of the molecular collisions. This is also termed as thermodynamic pressure. You have already read in thermodynamics that when any system is in thermodynamic equilibrium, so fluid at rest is in thermodynamic equilibrium, then the pressure exerted by the system is the thermodynamic pressure. So hydrostatic pressure and thermodynamic pressure is simply known as the static pressure in a fluid flow. But what happens when the fluid is flowing, this static pressure is sensed in a direction normal to the direction of velocity, normal to the flow velocity direction. And it will be proved in later sections, a chapter which we will be discussing afterwards, that in case of a class of real fluids known as Stokesian fluids, which obeys the Stokes law, that's why these fluids are known as Stokesian fluids. This law states that the second coefficient of viscosity, which I will be again describing or discussing while we will be discussing this viscous flow, that in case of Stokesian fluids, which obeys the Stokes law, the static pressure is the arithmetic average of the three normal stresses. Is the arithmetic average of the three normal stresses. Three normal stresses means three normal stress components, sigma x, sigma y, sigma z. If it is in x, y, z coordinates, then it is sigma x, sigma y and sigma z. If we take in x, y, z coordinates, then it is the arithmetic average of the three normal stresses. It will be proved the static pressure is the arithmetic average of the three normal stresses. Now let us consider a case like this. Well, if we consider a flow through a duct, let us consider the flow through a duct, with uniform velocity through a duct. Now the static pressure is sensed if we make a connection at the wall like this, and if it is connected to any pressure measuring device, Now this type of connection is known as wall tap, which measures the static pressure, wall tap. This is the flow direction. Now it is obvious that in this direction, the direction of the wall tap, that means along the axis of this hole or this connection, which is known as wall tap, there is no component of flow velocity. Flow velocity is in this direction. So this senses the static pressure. So another way of conceiving the static pressure is like this, that for example, if we have a duct like this, where the fluid is flowing, then if we just made a connection or wall tap and attach a piezometer, as you know what is a piezometer, then what happens? So the fluid at this section will rise depending upon the pressure here, and this is the static pressure because there is no component of flow velocity, and the height up to which it will rise, this height h will be the measure of the static pressure at this point above the atmospheric pressure, that is gauge static pressure. Now it will be also seen afterward that in case of a parallel flow, that means the flow takes place in one direction. For example, fluid velocities is there in one direction. Now there may be a velocity variation across this section depending upon whether the fluid is viscous or not. We consider a uniform velocity distribution, that is the hypothetical case, that is the case for ideal fluid. But in case of a viscous fluid, there may be a velocity variation. There may be a velocity variation with zero velocity at the wall, that is the most realistic condition, no slip condition. But in those cases, whether it is a real fluid or ideal fluid, then is a parallel flow, that is the flow velocity exists only in one direction, that is in this direction here. The static pressure remains uniform throughout the cross section. So therefore a wall tap which measures the static pressure at the wall theoretically, this measures the static pressure at the cross section itself, since it is uniform over the cross section. But in case of an real fluid, not parallel flow, not in case of a parallel flow where there is a chance that static pressure may vary across a section, then we have to insert a probe at a point where static pressure has to be measured. And what happens is that it is like that, a hole is made at the side of the probe, so that normal to the direction of the flow velocity we can measure the pressure. So this is connected to any pressure measuring device. So this is the way by which a static pressure is sensed in the flow of a fluid. So this is the concept of static pressure that we have defined. Now we will go to the concept of stagnation pressure, which is stagnation pressure. Now we will go to the stagnation pressure. Stagnation pressure. Stagnation pressure. What is stagnation pressure? Now what is stagnation pressure? Let us consider a duct like this. Let us consider a duct like this, where the fluid is flowing. For example, at this section, the fluid is flowing with an uniform velocity distribution. Consider an ideal fluid. So therefore uniform velocity. Sometimes in a real fluid we can make a situation where the fluid approaches a duct at uniform velocities. But while it comes in contact with the solid surface flowing through the duct, the flow velocity is not uniform for a real fluid. However, we consider a uniform flow considering an ideal fluid. Now what you think that if you now just consider like this, place a tube which is precisely a probe like this. We place a tube like this and we just attach it to a pressure measuring device. Pressure measuring device. So what is this? This is a pressure. This may be anything, a manometer, a piezometer, or any other pressure measuring device. It is not very important for us to go into detail of the pressure measuring device. Now what happened? The fluid, that this is like this. The fluid at any point here, if you consider a point parallel to the axis, this is a very short tube. Let me consider point A. Now what happened? Fluid is coming into this and it is closed at other section, this tube, pressure measuring. That means that when the fluid comes through this and ultimately comes into the pressure, it may be a manometer, so the fluid is brought to rest. That means if you consider this system, that means here within this tube we see there is a column, static column of or static mass of fluid. So if this point just after the entry to the tube, you consider B or any point, this may be here or here, if we neglect any pressure variation in that tube, it's a short tube, then at any point in the tube where the fluid mass is at rest and at any point A in the same plane where the fluid has a velocity V, that uniform velocity, if we write the Bernoulli's equation, considering the fluid to be ideal, that means there is no dissipation of mechanical energy into intermolecular energy, we can write that P by rho, Pa by rho rather, plus V square by 2 is equal to Pb by rho. That means the pressure here is more than that at A by this amount V square by 2. This is because fluid is at rest, and if we consider this pressure is same throughout this mass of fluid, that means this is the pressure that is being registered or measured here. So this will give an indication of Pb. So this Pb now we write it as P0. So therefore if we write Pb as P0 and A is a general point, any point which has a velocity, flow velocity V, then we can write this equation like this, V square by 2. Or we can write P0 is equal to P plus rho V square by 2. Now we see that this P0 the pressure which is created by bringing the fluid to rest is more than the static pressure which the fluid was having when it had a flow velocity v plus the magnitude rho v square by 2. So, this is a pressure unit. So, this is the corresponding equivalent pressure head corresponding to the velocity head v square by 2. So, this pressure P0 by definition is known as stagnation pressure. So, this is known as stagnation pressure. So, this is known as stagnation pressure and this is known as static pressure. This is known as static pressure as you know, and this part, this rho v square by 2 is known as dynamic pressure. That means this is the pressure which is created because of dynaming it. So, this equation tells a very simple physics that the entire kinetic energy at this point A is converted to pressure energy. That means when the fluid is at rest, the entire kinetic energy is converted into pressure energy, because energy conservation tells for an ideal fluid, viscousness fluid or inviscid fluid, total mechanical energy remains constant. So, therefore, a part of the kinetic energy, the full kinetic energy is converted to pressure energy, because there is no other form of mechanical energy in this static mass of fluid except the pressure energy. So, total conversion of kinetic energy into pressure energy. So, therefore, a stagnation pressure is defined in short that it is the pressure which the fluid will exert if it is brought to rest isentropically. If it is brought to rest isentropically, the word isentropically is used. As you know, the isentropic process is a process which is a reversible and adiabatic process. That means there is no heat transfer with the surrounding. Why? Because there should be another restriction, that when the fluid is brought to rest, then there should be a proper insulation into the tube. No heat transfer, no energy interaction should take place with the surrounding. Energy should not come in or energy should not go out. No question of work transfer comes here. So, only heat transfer can take place, and it is very simple from physical sense that when the fluid is brought to rest, that means the pressure kinetic energy is brought into pressure energy, but what happens that a part of this pressure energy, kinetic energy may be converted to heat and may be transferred to the surrounding. So, if it is made insulated, that no energy interaction is taking place between the system and the surrounding, and if it is free from any dissipative effect, which is known as a reversible process in thermodynamics, well, when there is no energy transfer with the system, between the system and the surrounding, and when there is no internal dissipation, the flow is known as a reversible, the process is known as a reversible process. And also if the adiabatic process is adiabatic, the entropy of the process remains throughout the process same, and the process is known as isentropic process. So, that is why the conversion from a flowing fluid to a static fluid for an inviscid fluid without any interaction of energy with the surroundings is known as isentropic process. So, therefore, the pressure which could have been experienced or which could have been exerted by the fluid or which could have been obtained from the fluid if the fluid is brought to rest isentropically is known as the stagnation pressure. But simply without going through all these details, we think that a stagnation pressure is that the static pressure plus the dynamic pressure. That means if I know that the static pressure of P at any section in a fluid flow and corresponding velocity is V, then the stagnation pressure is P by rho plus V square by 2. This is by definition. But the actual, now there is a difference, that the pressure which is measured actually for a real fluid, because an isentropic process is a hypothetical process, obviously an inviscid fluid is an hypothetical fluid. So, for a real fluid, the pressure which is measured when the fluid is brought to rest, for example, by inserting a measuring device with a probe like that, let this pressure is P0 dash, it is always less than P0. But this is not the stagnation pressure. So, literally we can think that fluid is stagnating, fluid is made to rest, and this is the pressure measured, that is the stagnation pressure. No, stagnation pressure by definition is this one. That means if it could have been brought to rest isentropically, that means mathematically if the entire kinetic energy could have been converted to pressure. Why this measured pressure for a real fluid when it is brought to rest is less than this? Because a part of the kinetic energy is converted into intermolecular energy due to the fluid friction, which will cause a rise in the temperature of the fluid. Because of insulation, the intermolecular energy, the rise in intermolecular energy may not cause in terms of heat transfer. That is a different issue. But a part of the kinetic energy will be converted into intermolecular energy. So we will not get the pressure as big as this, P plus rho V square by 2. So the measured pressure will be less than this. But stagnation pressure by definition is P by rho plus V square by 2. That means P0 is P plus rho V square by 2. This is the definition of stagnation pressure. So now the question of measurement of stagnation pressure comes if we place a tube or the sensing probe facing the direction of the flow, so that it can take the component of the flow velocity which is arrested and it is measured. But the measured pressure is never the stagnation pressure, but in loose term we tell it as the stagnation pressure. Now first, the concept, the idea of measuring stagnation pressure was given by a scientist known as Henry Pitot. The T is not pronounced, so it is pronounced as Pitot, P-I-T-O-T, Pitot, but it is pronounced as Pitot. Henry Pitot is the scientist who first discovered this and get the idea. Now first of all, let us appreciate the idea. Consider the flow with a free surface, that means flow in a river. Why? Because Henry Pitot first made this idea clear by measuring the velocity by this Pitot tube. So Pitot tube measured the velocity of the fluid. So the velocity of the fluid in a river, he first used this concept in a river where there is a free surface. It is very simple. At any point he just inserted a tube. It is a classical concept. This is done long back. So at this time this is nothing, but this was a great thing at that time. So he just, and what happens? The liquid in the river rises from the free surface. Obviously, if at any point it has to rise because it has a flow velocity. So therefore, it rises to a velocity h. Now the pressure here is equal to this height. That is the height from the free surface. So therefore, static pressure corresponds to this height of the fluid or the liquid here, water, from the free surface. So this height therefore is the extra amount from that static pressure. So this height is responsible for the stagnation pressure. So therefore, this is the measure of the stagnation pressure. Of course, not the stagnation pressure by definition, certain less than the stagnation pressure, but we will call this as the stagnation pressure. So this is the measurement of stagnation pressure. But what happens if the fluid flows through a duct? What happens if the fluid flows through a duct? Fluid flows through a duct, then the static pressure cannot be given by this difference height below the free surface. So in that case, a single tube cannot measure this h. Here we can write h. For example, if you write the equation P0 considering P plus rho V square by 2, if I consider this as the P0, rho G H, P0 minus P, so rho V square by 2 is equal to P0 minus P. We consider this as P0 minus P is, what is P0 minus P? Rho GH. Rho is the density of the fluid. So therefore, we cancel this. So V is equal to root over 2GH. But this is calculated on the basis of the ideal flow equations, and we take the H for the real fluid with the same logic as we have described earlier for venturimeter. We just multiply with a coefficient which takes care of the friction. So V is equal to C into 2GH, because this H is measured the head, that is the pressure difference in terms of the liquid jet for a real fluid. So C is root over 2GH. So V, this is the velocity, this is the correction factor we get. For a single tube we get this because P0 minus P is H. That is the difference height above the free surface. But in case of a duct, what happens? We cannot have this by a single tube. In that case, what we do? In case of parallel flow where the section, this is the static pressure at any section remains constant. So to find out the velocity at any section, what we do? We insert a pitot tube along with a wall tap, that is the wall tap tube. So these measures, for example, this is a piezometer, pressures are not very great. So this gives a pressure reading like that. Let this is H. That is the static pressure at this point, and if it is constant across this section for a parallel flow, then it is the static pressure at that section, means this point also. Now this is inserted at this point, so it gives the stagnation pressure which must rise because of the dynamic head to a height. Let this is the height H0. So here we will have to precisely take H0 minus H into rho g. Into rho g is the difference between the static and stagnation pressure. So therefore we will have to calculate this not with H0, sorry, H0 minus H rho g. Very simple. Now these two tubes were combined into a single tube to give a good measuring instrument today's use to a large extent, which is known as pitot-static tube, which is used today to a large extent in all laboratories, the simple measuring instruments for fluid flow velocity and finally the flow rate. As you know, if the velocity of fluid is found at each and every point, we can find out the flow rate. For example, if this is a uniform flow, you know the velocity. If you find the velocity v, then the flow rate is a into v. So determination of flow rate is nothing. If we know the velocity, we can find out. If there is a velocity variation, if we know the velocity at each and every point, then we can find out the flow rate by integrating the velocity and infinite small area in the location. So this thing you know. So therefore this pitot-static tube is widely used today in all laboratories to measure the fluid flow velocities or the flow rate. So these two tubes, as I have described, is made into a single tube to give. So this is the typical structure. The shape is like this. This is nose. So this faces the fluid flow, and this central tube is the stagnation tube. This known as stagnation tube or stagnation pressure measurement. Stagnation tube, which measures the stagnation pressure, So the fluid flows like this, so this part is the stagnation. There is no flow, there is a static fluid, and side this annular tube is the static tube. So this is the hole which sends the static pressure, and this is the static pressure tube. So these holes are at the side. So this is inserted. This is very small, but exaggeration. I have made this amplification for this clarification drawing. This is very small tube. These dimensions are negligibly small compared to the dimension of the duct, so that this does not put any disturbance to the flow field. Otherwise the flow field is disturbed. But however, whatever small this dimension may be, the flow field is usually disturbed. So what happens then? This part is connected to one end of the manometer and this part is connected to another end of. Usually a manometer is used in measuring the difference of pressure with a manometric fluid. In case of flow of liquid like water, oil, this is mercury. So therefore from the manometer deflection we can find out the pressure difference between this tube and this tube, that is the stagnation and static pressure, and we can find out the flow velocity. So this is simply known as pitot-static tube. Pitot-static tube measures the flow velocity, which is combination of the pitot tube for measuring the stagnation pressure, or this we can know simply pitot tube, which is the measurement of stagnation pressure, stagnation tube, pitot tube, along with the measurement of static pressure by the annular tubes through these surface holes. They are combined in a single instrument and known as pitot. It is nothing great, but it was discovered long back by the scientist Pitot, and it is named after him as pitot-static tube. All right. Now, after this, we will come to the next section, which is very, very simple: orifices and mouthpieces. Orifices and mouthpieces. This is the most simple chapter of this fluid mechanics, which probably requires the knowledge level of class 8 or class 9, I think so, nothing more than that. Orifices and mouthpieces. What is an orifice? Orifice, yes, please tell me if you have any query, please. Orifices and mouthpieces. Now an orifice, now what we will discuss, orifice is a small hole, sharp-edged hole or aperture in a tank or in a reservoir. First we will discuss the discharge through a orifice, discharge through an orifice from a tank under constant heat, from a tank or reservoir, whatever you write, they are same, from a tank or reservoir under constant heat. First I thought that it may not be taught in the class, but complete the course curriculum, This is so simple. Let us consider a tank where there is a reservoir at the side of which there is a small orifice. Let there is a small orifice. At the side of whom there is a small orifice. That means a small aperture or hole, whose cross section may be circular or may be of anything else. And this tank is maintained with a constant height. That means the height of the free water surface from the axis of the orifice, this is maintained constant. Let this height is h. How this is maintained constant? If the orifice, the water is discharged from the orifice, the water is also, there is an inflow of water. There is an inflow of water, so that the height is maintained constant. This is shown like this under constant height, that means which is known as head. This is the pressure head at any point to any point at this axis. Now what happens? The water comes out from the orifice. This is a very common experience. Now you will see the streamline converges like this. Streamline converges, and ultimately it forms a section where the streamlines gets parallel, and this is the section known as vena contracta. Let this section is CC. This is known as vena contracta. This is very close to the orifice, the downstream of the orifice, where it becomes parallel and then it falls against the gravity. This is the solid jet. So the streamlines are not visualized by naked eyes without giving any dyeing agent. It is coming as a solid jet. So it is obvious that the streamline, which was initially like this, flowing like this gets a change. The water from here, this takes a turn because it gets an aperture, that is a discharge exit area. So it takes a turn, and then ultimately it comes parallel again. There is a turn in the streamline, it gets parallel again, and it attains a minimum section which is lower than the area of this orifice. This section is known as vena contracta, then it comes out from the orifice. Now our concern is to find out the discharge through an orifice. How can we find out the discharge? We can apply the Bernoulli's equation at any point at the orifice, or vena contracta which is very close to the orifice. We will rather take vena contracta and a section here. Let this section is 1, 1. So now what is the pressure head at 1, 1? Please tell me, above the atmospheric pressure? 0. What is the velocity head here? 0. What is the datum head here? If now we consider the datum head, okay, from any reference datum, let this be Z1. So Z1 in terms of the head, energy per unit to 85, right? Then at this section, if we consider this axis, this is Z2, then we can write here the pressure is 0 Vc square by 2G plus Z2. So therefore Vc is equal to root over 2GH. It is very simple. But here what we have assumed? We have assumed the fluid to be ideal. Obviously, for an ideal fluid, this potential head or datum head is utilized to generate velocity. That is the maximum velocity generated at the minimum area. So this is in terms of the potential energy. Here at any point, this is in terms of the pressure energy. That means if we write the Bernoulli's equation here and here, same equation we will get. This is in terms of the potential energy. Sometimes we can choose a streamline, which has been done in my book, and take any point here as 1 and any point here in this cross section and use the Bernoulli's equation. Same thing you will get. So for this point you define a datum head, and for this point the pressure, static pressure will be the pressure corresponding to the height of the liquid above. And whatever way you choose the point, any 2 points, 1 point has to be in this section, vena contracta section. You always get this formula for an ideal fluid, that Vc is root over 2GH. This formula, Vc is root over 2GH for an ideal fluid, which is so simple, even a school level boy you will think this is so simple, was first found out by Torricelli, Torri, sorry, 2R, 2L, Torricelli's formula. This is known as Torricelli's formula for the discharge. But now, if the friction is considered, this is the ideal velocity, that is for an ideal fluid. Due to friction, the velocity will be reduced. Obviously, the entire potential energy will not be converted into kinetic energy, or pressure energy will not be converted into kinetic energy because of the fluid friction. So therefore, the Vc or the discharge velocity, which is Vc actual, that will be is equal to some constant into root over 2gh. This constant is known as coefficient of velocity. Now this coefficient of velocity depends upon the height or the head above the orifice, axis of the orifice, and depends upon the velocity. Discharge velocity is head, and same thing depends upon the geometry of the orifice. That means the area of the orifice and the shape of the orifice. Well, therefore now we can write Q as AC into Vc. Vc actual, now I can write Vc actual, that means is equal to AC into Cv, because I have got the actual velocity because I know Cv. Now this AC is the area of the vena contracta. We have already recognized earlier that coefficient of contraction is defined. Coefficient of contraction Cc is defined as A0 by AC, where A0 is the area of the orifice. Orifice is very small in dimension compared to the head or height of the water surface in the tank or the area of the tank, so that we are not now much bothered about the shape of the orifice. It is only the area A0. Why? The shape of the orifice and other things, because the entire orifice is at a height h. So the different points at the different locations of the orifice is not varying in its head h. So they are so small, so we are not bothered about its shape and anything. It's simply the area of the orifice A0. So ratio of area of the orifice to that of the vena contracta is Cc. So therefore we can write this Q is equal to Q actual is equal to, why I write Q actual, I will tell you. If I express the Cc into Cv into A0 root over. Therefore we see that the discharge from a small orifice at the side of a tank is given by, then Q is equal to Cd into the area of the orifice root over 2gh, where h is the height of the free surface above the orifice. For example, if this be the orifice, then this is the h, that means this is the free surface, well, and from the center line of the orifice, this is the height of the free surface from the orifice. So we have found that, or we have proved that the discharge rate of discharge through this orifice is given by Cd into area of the orifice root over 2gh, and the streamlines, if you see that we have just discussed like this converges to a small section, a smaller section, which is the vena contracta section, and then goes like this. So this is the vena contracta section, and this Cd, as we have seen earlier, is composed of the two things. One is the coefficient of contraction, another is the coefficient of velocity, which takes care of the friction and which takes care of the contraction of the streamline to a minimum area which is less than that of the orifice, and h is the height above the orifice, and orifice is so small that at each and every point is under the same height h from the free surface, so that each and every point on the orifice is acted upon by the same potential head h, so that the discharge coefficient is given by this formula, which is known as Torricelli's formula, that we have already appreciated. Now for a better understanding of these things which we have discussed so far, we will go through some examples. Well, let us start with the example number 1. So this is the first example. Let us see that what it is. Air flows through a duct and a pitot-static tube. This is an example with the stagnation pressure and static pressure problems, how to measure the velocity of a fluid and the respective discharge by a pitot-static tube. So again I start the problem. Air flows through a duct and the pitot-static tube measuring the velocity is attached to a differential manometer containing water. Well, if the deflection of manometer is 100 millimeter, that is the deflection of the manometer for the manometric liquid,
calculate the air velocity assuming the density of air is constant and equals to 1.22 kg per meter cube. This is the density of the air, and the manometric liquid is water attached to a differential manometer containing water. Water is the manometric liquid, air is the working fluid measuring the velocity attached to a measuring the velocity is attached to a differential manometer. Density of air, that means it is given, calculate the air velocity, that means the working medium is air, the flowing fluid is air, and the manometric liquid is water. Well, the density of the flowing fluid, that is air, is constant and equals to 1.22 kg per meter cube, and that the coefficient of the tube, which is very important, is 0.98. Now, how to solve this problem? So, let us now see that the problem, we draw this duct first. Let us see that this is the duct through which the fluid is flowing. Well, this is the duct through which the fluid is flowing, and let us see that this is the flow velocity. Let us represent the flow velocity like this, that means flow is in this direction. Flow is in this direction from left to right. Well, this is the direction of the flow, left to right. Now, a pitot-static tube is attached to this to measure the velocity at a point. So, therefore, now we will construct a pitot-static tube, or we will place a pitot-static tube. So, let us show that pitot-static tube like this. Now, this is a pitot-static tube. Let me draw, which has been drawn earlier also. We have shown the pitot-static tube earlier also. So, this is the typical pitot-static tube. This is the central part of the tube which senses the stagnation pressure. That means, this is facing in the direction of the velocity, and this is the typical U-tube manometer. Well, and this is the typical U-tube manometer. So, U-tube manometer, you just see that this is the pitot tube, pitot-static tube. Well, this is the pitot-static tube. Now, let you see that this is the typical arrangement, and you just show that this is the liquid column, that is the water, this is water. Well, and this is the deflection, delta H. Well, this is the deflection, delta H. Now, look that this central tube senses the stagnation pressure. So, this is high, so that this end is getting depressed and this end is going up. So, this is the delta H, the deflection in the liquid in the manometric tube. Well, and this part is filled with air. Now, here the pressure is the stagnation pressure. Here at any point the pressure is the stagnation pressure, that is P0. Here the pressure is P0, and here at any point which senses the static pressure, the pressure is P. P0 is the stagnation pressure, P0 is the stagnation pressure, and P is the static pressure, Well, now if we write the manometric equation, here one thing is that if we neglect the density of the pressure due to this column of the air in both the sides, because of the low density of air corresponding to that of the water, because the density of the air is 1000 times less than that of the water, so that we can neglect the air pressure due to this column of air very much, and we can tell that the P0 which is sensed here is just sensed at this level, and obviously the P, the static pressure which is sensed here through this tube, is sensed at this meniscus level. So that if we write the hydrostatic pressure equation considering this as the plane where the pressure is same in the same expanse of the liquid, as we have read earlier in the subject of hydrostatics, then we can write that this side pressure is P0 and this side pressure is P, that is static pressure, plus rho of W, that is the manometric liquid which is water, into G into H. Sorry, it is delta H. It is delta H. So, therefore, P0 is equal to P plus rho W G delta H. Well, so that we can get the difference in this stagnation and static pressure as rho W G into delta H. And in this problem, it is given water, so 10 to the power 3 is the density of the water, into the G is 9.81 into the delta H, which is given as, in the problem you see that delta H is given as 100 millimeter, the deflection of manometer is 100 millimeter. So, therefore, we can put it in terms of meter 0.1 and this gives us 981 Newton per meter square. This is the difference between the stagnation and static pressure. Now, if we write the velocity, we know that the difference in stagnation and static pressure, as we have recognized earlier from the definition of stagnation pressure, is the pressure equivalent of the velocity. That means, if the velocity at that location is v, then half rho v square equals to P0 minus P. This is the way the stagnation pressure is defined. That means, P0 is equal to P plus half rho v square. Well, so if we use this, then we get, here I write V is equal to root over 2 P0 minus P by rho. And this rho, mind that this is the density of the air, because when we write this equation, this comes from the Bernoulli's equation applied to two sections where the pressure is stagnation pressure, that section where the pressure is static pressure along with the velocity V. So, therefore, here the density which will come, that will be the density of the flowing fluid, that is rho of air. In this case, air is the flowing fluid. So, therefore, if you write V will be equal to, this is the theoretical velocity, I am sorry, this is theoretical velocity. So, the actual velocity actual will be multiplied with a coefficient, then C will be multiplied with a coefficient. Now, this coefficient is 0.98 as it is given in the problem. The coefficient of the tube, you can realize, you can see that the coefficient of the tube is 0.98. So, therefore, 0.98 times 2 into P0 minus P, already we have calculated earlier, 981 Newton per meter square, all right, divided by 1.22 is the density of air, which is also given in the problem, that this is the density of air, 1.22 kg per meter cube. So, that if you calculate this thing, it will come out to be 39.3 meter per second. So, therefore, you see the application that a pitot tube is attached or pitot tube is placed here to find the velocity at the local position, this local velocity at this position. So, the central part of this sends the stagnation pressure, the annular part of the tube sends the static pressure. This is attached to a differential manometer with a manometric liquid. Usually, when air is the working fluid, the manometric liquid taken is water. Well, so that we get a differential head, a difference between the meniscus level delta H, which is nothing but the difference between the stagnation and static pressure, which is again equivalent to half rho v square, where rho is the density of the working fluid, and from there we can calculate the velocity. This is the theoretical velocity, because this is the Bernoulli's equation where friction is neglected. So, this is being multiplied by a coefficient of the tube, which is the frictional losses in the tube, which depends upon the design of the tube. For a given fluid, it depends upon the design of the tube. So, for a tube, this is being calibrated so that the coefficient of this tube is given beforehand while calculating the actual velocity from this formula. Well, now next we will go to another example regarding the orifice, which we have Torricelli's formula, which we have just discussed. Example 2. This problem is like that. What is the diameter of a circular sharp-edged orifice required to discharge 0.01 meter cube per second of water, that is the discharge rate, under a head of 10 meter? Take the coefficient of discharge to be 0.6. So, it is a straightforward application of Torricelli's formula. As we know, the discharge through an orifice under a constant head in a tank is given by CD, that is the coefficient of discharge, into the area of the orifice into root over 2GH. All right, here it is a straightforward applications. We have CD is 0.6. Now it is a circular orifice, sharp edged circular orifice, so that the area of the orifice will be pi times d square, where d is the diameter of the orifice, by 4. So that we can write pi d square by 4. Okay, d is given, d we have to find out. I am sorry, d is not given. So h is given, under a head of 10 meter, h is given. So our problem is to find out d. That means we have to apply this formula straightforward to get d. Well, let us do that. Now q is also given. Q is 0.01 meter cube per second. All right. So I write q is equal to 0.01 is equal to CD is 0.6. Okay. Then the area is pi d square by 4. All right. Then root over 2, G is 9.81, and H, the head is 10 meter, 10. Now this we write, all the values are given, only the value of D has to be found out. So if one makes the calculation, he will get D from here as 0.04 meter, which is equal to 40 millimeter. So therefore we see, for a circular orifice, a 40 millimeter diameter is required to discharge this much, that is 0.01 meter cube per second of water under a head of 10 meter. This is the direct application of the Torricelli's formula, that the rate of discharge is given as CD into A0 into root over 2GH. Now here I like to mention one thing, that in this equation Q is equal to CD into A into root over A0 into root over 2GH. The liquid property, that is the density and the viscosity, is not coming explicitly. You see, that means whatever may be the liquid, Q, that is the discharge rate, can be found out if I know H and if I know the discharge coefficient of the orifice. Now the question comes, how then the density and viscosity is a very important property, comes into picture, because obviously this comes from our common sense, that when different fluids are used or liquids are used with different viscosities, even under a given head, the discharge rate will not be same. So the answer to this question lies in the fact that the CD is a function of the viscosity. Usually CD becomes a function of the Reynolds number, where the Reynolds number contains the viscosity and also the density. So this is a function of Reynolds number. That means this is indirectly a function of the density, viscosity, and the liquid head height and all these things. So therefore we see the viscosity and density, these two liquid properties, are implicitly expressed through the coefficient of discharge. Usually when the Reynolds number is low for a high viscosity liquid, then the value of CD is low. So one will expect then, in that case, the actual discharge for a given head or given height for that liquid through orifice of given area will be less because of the fluid friction. Because if you recollect, this CD is composed of Cc into Cv. So Cv is the coefficient of velocity, which takes care of the fluid friction. So for a given orifice, the fluid friction depends upon the viscosity of the fluid. For a sharp edged orifice, the friction at the orifice edge is very small, but nevertheless the friction losses are there, and also because of the motion in the tank, so that the value of Cv is taken care of. The value of Cv takes care of all these things, which may change due to the change in the viscosity of the fluid, so that with the Reynolds number the CD changes, and therefore these two properties rho and mu are inherent in this definition of the CD. Okay. Then we see a straightforward applications of this circular sharp-edged orifice required a given discharge under a given head. So next we will come to another thing, is that very important thing I like to discuss in this context is the loss of stagnation pressure, loss of stagnation pressure due to friction, friction, loss of stagnation pressure due to friction, which is an important thing. I must tell that how the stagnation pressure is reduced due to friction. Let us consider the flow through a convergent duct. It is not necessarily to be a convergent duct, but let me consider a convergent duct for our simplicity or for our better understanding, and let us consider two sections. Let us consider two sections 1 and 2, and at section 1 let the pressure is P1 and the velocity is V1, and at the section 2 let us consider pressure is P2 and velocity is V2, and we consider the flow so that no heat or work transfer takes place, no heat or work transfer. That means the flow is adiabatic, there is no heat transfer and no work transfer. That means from outside there is no interaction in the form of energy transfer with the fluid. Neither heat is added nor heat is rejected, neither work is added nor work is rejected. So then what happens if we write the Bernoulli's equation in case of a frictionless flow, 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 and if we consider the change in the datum height is negligible between the section 1 and 2, or in case of an horizontal convergent duct, then we can write P1 by rho plus V1 square by 2 obviously is equal to P2 by rho plus V2 square by 2, because there is no loss, and moreover the datum head, the potential head is negligible or their change is 0. And these two things equals nothing but the P0 by rho. That means where P0 refers to the stagnation pressure at these sections and at this section. That means the stagnation pressure at this section and this section remains same, which means that the stagnation pressure is not changed if the friction is not there. This is the same thing that if we tell that the stagnation pressure is the equivalent total mechanical energy except the kinetic energy. That means stagnation pressure referred to the pressure equivalence or energy equivalence pressure, mechanical energy equivalence pressure if we discard the kinetic energy part. So long the if we discard the potential energy part. I am sorry, if you discard the potential energy part. That means if the potential energy changes are neglected, then the total mechanical energy remains same in a frictionless flow, so that the stagnation pressure remains same. But if you consider a viscous flow, which happens in reality, if you consider a viscous flow, and in that case if I define P2 dash is the pressure here and V2 is the velocity. Velocity will remain same. Why? Because of continuity. If area of cross section here is A1 and the area of cross section here is A2, then because of the continuity we can tell V2 is A1 by A2 into V1. Alright, V2 is A1 by A2 into V1. So therefore, from the continuity the average flow velocity will remain same. Then what will happen in that case? P1 by rho plus V1 square by 2, if I write the Bernoulli's equation, then this side it will be P2 dash by rho plus V2 square by 2 plus the frictional head loss HA, which is loss due to friction. That is a part of mechanical energy converted into intermolecular energy, which means that P2 dash is less than P1. This we have recognized. Now, therefore, we see that the stagnation pressure corresponding to this section is this total mechanical energy, that is except the potential energy, that is P0 by rho, whereas the stagnation pressure at this point, if we define it as P0, this is P01, P02 dash divided by rho, then we see that P02 dash is less than P01 dash, because this is less than this by this amount HF. That means we can write that P02 dash is P01 dash minus HF. That means the stagnation pressure is reduced because of the friction, and the reduction is equivalent to, I am sorry, in terms of rho, that means you have to multiply rho here. Otherwise, if you express in terms of the stagnation pressure head by rho, then it will be simply HF. That means the stagnation pressure or stagnation pressure head is reduced by the amount which is equal to the frictional head loss or the energy loss due to friction, mechanical energy loss due to friction. So this is the concept. The stagnation pressure remains unchanged if the flow is inviscid or frictionless flow. There is no dissipation, and provided there is no interaction of energy from the outside. This happens in case of an adiabatic flow and without friction, and this is known as isentropic isentropic flow. Afterwards, in the study of gas dynamics, we will see that in isentropic flow, the stagnation pressure remains unchanged. This is the theory. But when friction comes into picture, the stagnation pressure is reduced by the amount which equals to the head loss due to friction or energy loss due to friction. So, this is an useful concept, that a stagnation pressure goes on changing because of the friction. Okay. Then I think today up to this we will discuss the next thing, the next class. Okay. Then thank you.